Structure, bonding, and hybridization. In this section, we'll explore the history behind organic chemistry and understand why organic compounds are so important in our world. In the early 1800s, scientists thought that there was a clear distinction between organic and inorganic compounds. Organic compounds were believed to come from living things and contain a special vital force, whereas inorganic compounds were thought to come from non-living mineral sources. Chemists at that time assumed that they could not create organic compounds in the lab since they could not create life itself. But in 1828, the German chemist Friedrich Euler surprised everyone by making urea, which is an organic compound from inorganic starting material, ammonium cyanide. This showed that organic compounds did not require a special vital force after all. Now, after Euler's discovery, chemists had to rethink how they define organic chemistry. They decided to define organic compounds simply as those containing the element carbon. And it turns out that the molecules essential for life, like proteins, DNA, and carbohydrates, are all organic compounds. And also the chemical reactions happening in living things, including our own bodies, involve organic chemistry. But organic compounds are found in many other places too, like our food, clothing, and energy resources. In fact, there are currently around 16 million known organic compounds, with many more possible that we can't even imagine today. Organic chemistry touches every aspect of our life, from the molecules of life to the materials we use daily. And one thing that is common in all of these organic compounds is carbon. So we have to understand why carbon is special. Now, the answer for this is going to come from carbon's position in the periodic table. As a central atom in the second row, carbon is not going to accept electrons or give off electrons. Instead, it is going to share electrons with the other atoms, including other carbon atoms. And this ability to form stable covalent bonds allows carbon to construct an incredible diversity of molecular structures, from simple hydrocarbons to complex biomolecules. When we study organic chemistry, we learn how these carbon-based compounds react. Organic molecules are held together by chemical bonds which can break and reform during reactions. And understanding the behavior of these bonds and the electrons that form them is key to mastering organic chemistry. Structure of an atom. An atom consists of a tiny dense nucleus which is surrounded by electrons that are spread throughout a relatively large volume of space around the nucleus, which we call as the electron cloud. The nucleus contains positively charged species which are called as the protons, and a neutrally charged species which are called as the neutrons. And therefore, the nucleus is going to be positively charged, and the electrons are negatively charged. The amount of positive charge on a proton is going to be equivalent to the amount of negative charge on an electron. And therefore, the number of protons and the number of electrons in an uncharged atom is going to be the same. And keep in mind that electrons move continuously. Like anything that moves, electrons are going to have kinetic energy. And this energy is what counteracts the attractive force of the positively charged protons that would otherwise pull the negatively charged electrons into the nucleus. When coming to the masses, protons and neutrons have approximately the same mass and are about 1,800 times more massive than an electron. And therefore, most of the mass of an atom is going to be resting in the nucleus. And most of the volume of an atom is going to be occupied by electrons, and this is where our focus will be because it is the electrons that forms chemical bonds. The atomic number of an element is the number of protons in its nucleus. The atomic number is unique to a particular element. For example, the atomic number of carbon is 6, which means that all uncharged carbon atoms are going to have 6 protons and 6 electrons. Atoms can either gain electrons and become negatively charged, or they can lose electrons and become positively charged. But the number of protons in an atom of a particular element never changes. Isotopes. Although all carbon atoms have exactly the same atomic number 6, their mass numbers are going to be different. The mass number is the sum of number of protons and number of neutrons. So here, as described earlier, the atomic number is going to be the same, which is the number of protons that is going to be existing in a particular atom is going to be the same. But the only thing that is going to be changing in this is going to be the number of neutrons. And because there is a change in the number of neutrons, the mass number is going to change. Okay, so accordingly, we have carbon 12, carbon 13, and carbon 14. Distribution of electrons in an atom. According to Schrödinger, the electrons in an atom can be thought of as occupying a set of concentric shells that surround the nucleus. The first shell is the one that's closest to the nucleus. The second shell lies farther from the nucleus. The third and higher numbered shells lie even farther out. And each shell is going to contain subshells known as atomic orbitals. And each atomic orbital has a characteristic shape and energy and occupies a characteristic volume of space. The first shell consists of only an s orbital. The second shell consists of s and p atomic orbitals. The third shell is going to consist of s-p-d orbitals. And the fourth and the higher shell is going to have s-p-d-f atomic orbitals. There is one s orbital. There are 3 p orbitals, there are 5 d orbitals, and then 7 f orbitals. And the maximum number of electrons that can go into the orbital, into any orbital, is going to be 2. And because the first shell has got only s orbital, the maximum number of electrons that can occupy in the first shell is going to be 2. Whereas in the second shell, we have s orbital and as well as the p orbital. And remember, we said that there are going to be 3 p orbitals. And therefore, the maximum number of electrons is going to be 4 times 2 because there are totally 4 atomic orbitals. That's going to be equivalent to 8 electrons. And in the same way, the third shell is going to have s, p, d orbitals. So there is one s orbital, there are 3 p orbitals, there are 5 d orbitals. All together, there is going to be a total of 9 orbitals, and the maximum number of electrons that it can occupy is going to be 9 times 2, which is going to be 18. And in the case of fourth shell, it's going to be a total of 32. This chart right here gives the electronic configuration of some of the smallest atoms. So the first atom that we have is hydrogen. Hydrogen has got one electron, and that one electron needs to go into the 1s orbital because that's the one that has the lowest energy. And the second atom is helium. Helium has got 2 electrons. Those 2 electrons can be going on to the 1s orbital because the 1s orbital can occupy a maximum of 2 electrons. But when they go, then the electrons need to have opposite spin. Beryllium has got 4 electrons, so this is going to have completely filled 1s and as well as 2s orbitals. And then boron has got 1 electron in the 2px. And when it comes to 2px, 2py, and 2pz, all these atomic orbitals are going to be degenerate. So when we say degenerate, they're going to have exactly the same energy. So when we have orbitals which are going to have exactly the same energy, we need to make sure that we fill the orbitals at least with 1 electron each before we pair it up. And that's exactly what we are doing here in the case of carbon. So we try to put 1 electron into px, and then the second electron is going to go on to 2py. And because we don't have any more electrons, we are just going to leave it like that. But we can't pair this one. We can't pull this electron onto this orbital because pairing is not possible until all of these orbitals are filled with at least 1 electron each because they are degenerate. And the meaning for degeneracy is they are going to have exactly the same energy. Here are the rules for filling the electrons in different orbitals. We have 3 important rules. One is Offer principle. Second one is Pauli's exclusion principle, and a third one is Hund's rule. According to Offer principle, an electron goes into the atomic orbital with the lowest energy first and before filling the highest energy orbital. For example, like if I have the extra electrons after filling the 1s orbital, then I have to go into the 2s orbital before filling the electrons in the 2p orbital. The next principle that we have is Pauli's exclusion principle, which states that no more than 2 electrons can be in an atomic orbital. So that is the maximum number of electrons that can go into any atomic orbital. The third important rule is the Hund's rule, which states that an electron goes into an empty degenerate orbital rather than pairing up. Let's take the case of p orbital. There are 3 p orbitals, which are going to be designated as px, py, and pz. Now let's imagine that I have a total of 4 electrons. If I need to fill these 4 electrons in these orbitals, then first what I should do is I should fill each of these orbitals at least with 1 electron. Okay. Now I have used 3 electrons. Now the 4th electron can be used to pair up the first orbital. Okay. So unless each of these orbitals is going to be filled with 1 electron, pairing doesn't happen. And these are the rules that we needed to follow in order to fill the orbitals with electrons.